Welcome to Homework Lib.
This question is in reference to two radioactive isotopes. You are given the rate constants for the two radioactive isotopes, and if you look carefully, you will notice that the rate constants have units of 1 over a time, 1 over years in one case and 1 over days in the other case. Because they have units of 1 over time, they are both first-order processes. All radioactive decays are first-order processes. Because they are first-order processes, then we can use the first-order half-life equation to solve for the half-life of each of them. For Americium-241, the half-life equation for first-order processes is natural log of 2 divided by k, which is provided at 1.6 times 10 to the negative 3, 1 over years. This then gives us a half-life of 433 years. For iodine-125, it's the same equation, so it'll be T1/2 equals natural log of 2 divided by its k value, 0.0111 over days. So because the k value is now in 1 over days, then the units for the half-life will be days, and we get 63 days. Next, it wants us to, in relative terms, determine which decay occurs faster. Well, hopefully it's very obvious to you now with a half-life of 433 years for one of them and 63 days for the other one, that the 63 days, namely iodine-125, is the decay that occurs much more quickly than the americium decay. So the americium, thank goodness, is going to last many years in your smoke detector. For the next part, it wants to know how much of the 1 milligram sample of each isotope remains after 3 half-lives. Well, if you recall, after 3 half-lives, we have cut it in half 3 times. So after 1 half-life, we have 1/2 of the 1 milligram. After 2 half-lives, we have 1/4. After 3 half-lives, we have a half of 1/4, 1/8. So after 3 half-lives for both of them, we have 1/8 of the milligram left, recognizing that 3 half-lives for americium is going to be a lot longer than 3 half-lives for iodine. 1/8 of 1 milligram is 0.125 milligrams. The last part of this question then asks how much of the 1 milligram sample of each isotope remains after 4 days. Well, because they are first-order reactions, then we simply need to use the first-order integrated rate law in order to determine the amount that remains after 4 days. The first-order integrated rate law can be rearranged in such a fashion that the natural log of the concentration at time t equals negative kT plus the natural log of the concentration at time 0. So let's do americium first. Natural log of concentration, or the amount, at time t, namely 4 days, will be equal to negative k, which is 1.6 times 10 to the negative 3, 1 over years, multiplied by the time in years. So if 4 days pass, we have 4 365ths of a year. We'll then add on the natural log of the amount at time 0, which is 1 milligram. This allows us to solve for the natural log of the amount at 4 days. And then we take the anti-log of both sides, and we get x, which ends up being 0.99998 milligrams. So essentially, we have the same amount as we started with, namely 1 milligram to 3 significant figures, 4 days after. Now let's do it for iodine-125. The setup is the same. We're just using a different rate constant. And because the rate constant has units of 1 over days, we simply plug in 4 for the days, get the natural log of the amount, take the anti-log of both sides, and we get 0.957 milligrams of iodine 125 after 4 days.